Welcome to this presentation about exploratory data analysis in AI. The first step of the presentation is about data exploration, where we describe and display and summarize the data we're going to be working with in this project. This first step shows a few columns of the data we're going to be working with: the IDs, the radius mean, the texture mean, the perimeter mean, area mean. Just a few and some summaries about the number of columns and the rows in the data. These are the column titles of the various fields we're going to be working with, and the number of the columns is 32. The aim of the project is to make a model to diagnose whether a particular tissue or group of cells is cancerous or non-cancerous, and for this we have 357 non-cancerous cells and 212 cancerous cells that we're going to use to train and test the model. The first step, we convert the column of diagnosis from cancerous and non-cancerous to ones and zeros, 0 representing non-cancerous and 1 representing cancerous. That's the label encoding stage. And afterwards, this preview of the new table shows in this diagnosis column that those that are cancerous have now been replaced with ones instead of the actual word cancerous, and those that are not are replaced with zeros instead of the word non-cancerous. Our first illustration is a heat map with the very light areas showing a high correlation between some of the fields and a darker area representing a low correlation. The heat map is from this table. This table shows us how the different fields and the different qualities of the cells correlate, and the ones we're particularly interested in are those between the different fields or the features and the diagnosis. So as we can see, radius mean, perimeter mean, area mean, concave points mean, they're all highly correlated to the diagnosis, whereas smoothness mean, fractal dimension mean, texture SE, they're inversely correlated with the diagnosis. So we're going to be looking at some of those features to see how they differ between cancerous cells and non-cancerous cells. So our next plot is a correlation matrix, and this is between those features that highly correlate with the diagnosis or with cancerous cells. And this is radius mean, perimeter mean, area mean, and concave points mean. As you can see, with increasing radius mean, the diagnosis changes from 0 to 1, or from non-cancerous to cancerous. Same story for radius mean and the area mean. On the other part, those that are inversely correlated, you can see that with increase in fractal dimension, symmetry, and smoothness mean, there isn't much change or determination between if a cell is cancerous or non-cancerous. It's just scattered. Then we have our box plots, starting again with those that highly correlate. Here you can see that the perimeter mean on the part of the cells being cancerous has higher quartiles, has a larger interquartile range, higher median, and even the outliers and the maximum and minimum points are higher than those that are non-cancerous. This again shows that perimeter mean and area mean are highly correlated to, or highly determine, whether a cell is cancerous or non-cancerous, and with increasing perimeter mean and area mean, the chances of the cells being infected are greater. On the other hand, the fractal dimension mean and symmetry mean are still showing the inverse relationship, showing that when the cells are non-cancerous, the interquartile ranges are fairly equal to those that are cancerous, and there isn't much distinction between the maximums and the minimums, further showing their inverse relationship. A few patterns of interest here, despite alongside them being highly correlated with cancer, the perimeter mean at a certain point determines the area mean. So as the perimeter mean increases, so does the area mean, and with that, the chances of cells being cancerous also increases. And area mean can also be shown here to be inversely proportional to the fractal dimension mean. As you can see, with increasing area mean, with increasing fractal dimension mean, the area mean decreases, shown in this line plot. The gradient is inverse, and so as the fractal dimension mean increases, the chances of the cells being cancerous decreases because area mean is directly proportional to the cells being cancerous. With area mean and fractal dimension mean, there are a few outliers in that it's not conclusive that with increasing fractal dimension mean that we should rule out the possibility of the cells being cancerous, but a few times it doesn't follow suit, as you can see with some of these outlier plots. On to the next part of training and testing the model. First, we create our X values. We drop the ID column and diagnosis column, because as you're training, you don't want the model to know the final diagnosis. That's why we remove this column. Then the Y is just the diagnosis for comparison. So we split the data into a test and train split. We reserve 30% of the data for testing, so the other 70% is going to be for training, and we give it a random seed 42 to randomize the splitting. The model we make is a support vector classifier stemming from support vector machines, and we fit the model at this stage with the training data. Then we go ahead to predict. We go ahead to make predictions with the model we've just made using the testing data. After making a prediction, we compare the two, the tests and the predictions that we've just made, and we can see that at this point, the accuracy of the model is 93%, or 0.9357. We move forward to hyperparameter tuning. Hyperparameter tuning is the improving of the accuracy of a model by selecting the best parameters for or the best features for its hyperparameters. Hyperparameters are not learned by the machine, but they are set by the developer before training. So for this, we're going to use a grid search CV. Grid search CV is scikit-learn's hyperparameter tuning model. It's what we're going to use to improve the performance of our initial support vector classifier. So with this, we select our best parameters, which are 3 of the features that we've been using, and then go ahead to make the tuned version of our support vector classifier, fit it once again with the training data, predict against the testing data, and calculate the accuracy score. With this, we can see that the accuracy has been increased or improved to 97%. And that's it.